Hello, it's Keith here, and this is lesson 4 of the Mips Assembly programming tutorials. We're going to be looking at some more commands today, and all the commands we're looking at today work with bits in some kind of way. Now there's two kinds of operation we'll look at: logical operations, which do command setting and clearing of bits, and also shifting, which surprisingly actually allows us to also multiply and divide by 2, as well as shifting bits around within the registers. So these are what we're going to be looking at today, and as always we're going to be looking at them by example. So let's get over to our source code and let's take a look. Okay, so this is the file we're going to be working with today. It's the lesson4.asm file, and as always we've got some jumps at the start. The first one for logical operations and the second one for bit shifts, and the first one we're going to have a look at right now. So what are logical operations? Well, these are commands that work with basically two parameters as the source parameters, and then as often with the MIPS processor we have a destination. Now logical operations take these two parameters and they perform some kind of surprise logical operation on them, and the result will vary depending on the operation that we perform, and we're going to see a variety of operations and see how the results come out. So the first one we're going to look at is XOR. Now this stands for, I believe, exclusive OR, and that might sound a bit alien to you either as XOR or exclusive OR, but we're going to explain it in just a moment. Now first of all, let's look at the two options available to us. The first is XOR as a command. A0 on the left, the first A0 is the destination, and then the second A0, the middle one there, is the source, and A2 on the right there is the second parameter to be applied to A0 there. The second one, XOI, the left hand side parameter A1 there is the destination, as pretty much always the left hand side is the destination, and then we've got A1, and then we've got an immediate value of FF in hexadecimal, and that is why the second command is XORI, XOR immediate, rather than XOR with a register. So the XOI allows one of our parameters to be an immediate. Now it wouldn't make any sense for both of our parameters to be an immediate, because if they were both immediates the result would always be the same. It doesn't make any sense. So we don't need that option, of course. So what does XOR mean, and what are these logical operations? Well, as I say, all of these commands will have a result destination and two parameters and a logical operation, and what these do is they will set the bits in the destination at the bit level according to the bits in the two sources. So each bit from bit 0 to bit 31 in a 32-bit register will be compared with the two parameters, whether one of those parameters is an immediate or both registers, and the bits in the final destination will apply according to the two parameters and the operation. Now the most simple one would be the AND command, and if we've got a parameter A and a parameter B and we use the AND operation, this will say if a bit in A and a bit in B is 1, the result is 1. Otherwise the result is 0. And so you can see here that in any case where both parameters do not contain a 1, the result is a 0, because it's an and requires both A and B to be 1. OR is similar, but unsurprisingly, OR will set the destination when either A or B is 1. So you can see if both are 0, the result is 0, but if either one is 1, the result is 1. XOR, the one we're looking at right now, this will actually flip the bits. So we will basically flip the bit of A if the bit in B is 1. So where both are 0, the result is 0. When A is 0 and B is 1, that A gets flipped from a 0 to a 1, and the result is a 1. When A is 1 and B is 0, then the 1 is passed through unchanged, and when A is 1 but B is 1, the 1 in A gets flipped to 0. Now the final one we have on this system is a bit odd. It's NOR, which stands for not OR. Now this is effectively the opposite of OR. OR would set the bit when either A or B is 1. NOR will set the bit when neither A or B is 1. So you can see here when both are 0, the resulting bit is 1. When either the bits in A or B is 1, the result is 0. Now you'll see there's bit here, bit clear, but that isn't actually included on this system. This list of examples here includes the bit clear, which doesn't exist on the MIPS processor. Anyway, so that's what we're going to be seeing today. And so when it comes to this XOR, this basically a bit flipping operation, we'll see how this has actually affected things. Now, in all of these examples, we've loaded these nice simple numbers here, 1, 2, 3, 4, 5, 6, 7, 8. These are, of course, nibbles. Each of these digits is 4 bits. And then we've created a mask here, and the top 4 nibbles here are F, and the bottom 4 nibbles are 0. And of course, a nibble of F means all of the bits were 1. And as I say, all of these commands work at the bit level. And so we will see these digits change as the mask in A2 is applied to them. So, for example, when we do an XOR of A0 with the mask in A2 and store the results in A0, our 1, 2, 3, 4, 5, 6, 7, 8 becomes an EDCB 5, 6, 7, 8. Now, the bottom 2 bytes are unchanged because the bottom 2 bytes of the mask here was 0. But the top bits, the top 2 bytes, have been flipped because all of the bits were flipped in it because of that FFFF there. So that XOR has flipped basically the top 16 bits of A0 there. That's what we have effectively done there because of that value in A2. Now the second example, we used the immediate, and the immediate value was FF. Now there is a limit to the range that this immediate can contain. But if we only need to do 1 byte, and often we might be working with bytes, if we're reading in data from hardware and masking out the bits we want, or flipping the bits or setting the bits we don't want, you can see here we've basically done a flip, and sort of coincidentally almost, flipping all the bits of a nibble with a 7 in it has converted it to an 8, and flipping all the bits of a nibble with an 8 in it has flipped it to a 7. Of course, this entirely depends on the configuration of the bits we're using. If we change this FF to an immediate value of 1 here, and we run again, well, we will get a completely different result. Let's see what happens this time. Well, the nibble with the 8 in there, you can see the 7, 8. The 8 nibble basically only has the top bit of the 4 bits in that nibble set to 1, and so when we flip the bottom bit, that becomes a 1 as well, and that converts the nibble that had a value of 8 to a value of 9 there. So seeing these values as hexadecimal makes it easy to see how this mask is being applied, but as I say, these are all applying at the bit level. So if you're struggling to think in individual bits, maybe check the hexadecimal calculator in Windows and see what these values will have. And as I say, when you think of it from the point of view of these truth tables, I think it will start to become clearer what is actually going on. So that's XOR, and that is really an ideal command designed for flipping of bits in registers when you need to do that. Now we have 2 commands that really I tend to think of as being sort of opposites of the same kind of task. Now the AND command is basically in a lot of ways used for setting bits to 0, because where a bit in the parameter that is the second parameter, A2 or that immediate, is a 0, it will be cleared in the destination, otherwise it will be left unchanged. Alternatively, OR does the opposite. Where a bit was 1 in the parameter, it will be 1 in the destination, otherwise it will be unchanged. So AND can be used for clearing bits, and OR can be used for setting them, and we'll see that right now. Okay, so we had our original values in A0 and in A1, and then next what we've done is we've done an AND with the same mask in A2, and we've done an AND with the immediate FF. And as I say, where the bit is 1, it will be kept. Where the bit is 0, it will be cleared. So our EDCB has been left unchanged, but all of our bottom bits have been cleared because the bottom bits were all 0, and so those have been lost there. In the same way, A1, because we passed a parameter of FF, the other 24 bits have all been cleared down to 0, and we're just left with the bottom byte there. So as I say, AND is great for masking out and removing parts of registers when you don't want them. Now, what we've done next for clarity is we've changed our value in A2 to the value CD. We set the top byte to CD and left all the other bits to 0. We're then going to use the OR command, which, as I say, will leave a bit unchanged where the bit is 0 in the parameter, and it will set it where it is not 0. Now, by using this mask of CD here, we have basically set the top byte of the A1 register here to CD because we had CD here. The second example, where we used an immediate byte, that has effectively set the bottom byte of A0 here. Now the limit of the immediate is a 16-bit value here, so we can use CD00 here, and that will work just fine. But if we try and use a value larger than that, so if we put in, for example, 1 CD, which would be 17 bits there, and if we run this again, you will see we get an immediate value error. It's out of range, we can't compile it into that command. So if we wanted to use a value larger than 16 bits as the immediate, we would have to not use the immediate, we'd have to load it into another register. So anyway, that's how we can use the AND, OR and XOR, which are the most common ones. And as I say, the MIPS does surprisingly bless us with this rather unusual neither A or B, or the not OR if you prefer. And as I say, this will basically set the bits where neither of the two parameters are 1. So what we've done here is we've loaded this A2 with the top byte as F. We've loaded A1 with the bottom byte as F. And then we've done a NOR of A1 and A2 and stored the result in A0. Now, there is no version of this that works with an immediate value, but most processors don't have it anyway, so I don't think we can complain. Anyway, because this will set where neither of the parameters are A1, the result is that the bits that were not set in either have been set to 1, so the middle bytes have become F, 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 F there. Neither of the two parameters. Now, the final thing we're going to mention, just as the Savannah we mentioned, is the NOT command. Now, the NOT command will flip all of the bits in a register, and this is effectively the same as doing an XOR with a parameter where the second parameter is basically 8 Fs, if you think of like a 32-bit parameter there. And so this will effectively flip all of the bits in A1 here and store the result in A0. And so you can see A1 contained 1, 2, 3, 4, and the top nibbles were 0 there. The top nibbles are now F, 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 and the 1, 2, 3, 4 has become E, D, C, B. And as I say, that is effectively the result of flipping all the bits there. And suffice to say, if we did 2 consecutive NOTs on the same register, the register would end up with the same value because, as I say, it is a bit flipping operation. So there we go. So that's all of the logical operations we're going to discuss today. We're going to now have a look at bit shifts. Now, bit shifts, as I say, have a surprising use, especially in 8-bit, where we have no multiplication and division commands, that they allow us to multiply by 2 every time we shift to the left. If we shift all the bits in a register to the left, surprisingly, it will multiply by 2. If we shift them to the right, surprisingly, it will divide by 2. And that is always true, provided 2 things. Firstly, that we are not going out of range. So if we had a very, very high number that was at the absolute limit of a 32-bit register, and we shifted to the left, some of the bits would get lost, and so the new value would not be twice the original one. And if we shifted the value 3, for example, to the right, it would become the value 1. We would lose the we'd lose the fraction there. So that is a limitation there. Finally, the other thing is signed numbers. We do need to consider the sign, because a negative sign number, we need to make sure we're preserving the sign if we're shifting bits to the right, and we have special commands to do that. That's what we're going to discuss now. Now, we do have 2 kinds of shift command. We have what's known as logical shifts, and these effectively are designed for unsigned numbers. Now, when we shift to the left, the bits will all go to the left, and any new bits that appear at bit 0 will become a 0. When you shift to the right, the new top bits will become 0 as well. So this will work fine for unsigned numbers, but for a signed number this would cause a problem. If you think of -1, all of the bits in the value -1 in a register will be 1, but if we shift that to the right and put a 0 at the very top, this will effectively become a very large positive number. It will no longer be a negative number in assembly. And so what we actually want to do when we shift to the right, if we want to halve a number, is we want to shift all of the bits to the right, but we want to keep the top bit the same as it was before. If it was a negative number, it will stay a negative number, and if it was a positive number, that will put a new 0 in the place, and it will keep the sign in both cases. So we have the concept of logical and arithmetic shifts. Now, a shift left will work in either the case of a signed or an unsigned number, because in both cases we would want to put a new 0 in the register bit position 0. But for a right shift, we need to use a logical shift for an unsigned number, and we want to use what's known as arithmetic shift for a signed number, and that will preserve that top value. So how do we do this? Well, we've got 2 kinds of command. We've got a command that will use an immediate shift amount. So if we wanted to shift the value in A1 to the left by 1 bit, we would use SLL for shift left logical, and that will store the value in A1 shifted to the left by 1 bit, and it will store it in the destination, that register on the far left, A1 again, and so that will shift by 1 bit. But if we want to specify a shift by an amount in one of our registers, we would use the SLLV, and the V you could think of as value or variable, and that will use a register as the amount of bits to shift. Now, coming from the 8-bit world, that would be a deranged luxury to me, but I'm sure there's loads of cases that's very handy, but as I say, for me, I'm always used to working with immediates anyway. But we're going to try both out here, and we're going to try shifts logically to the left and shifts logically to the right of our test value. And here is our test value, and we'll see how its bits change as we do repeated shifts. Okay, so here's our value in A0, and we're going to shift it to the left in A1, and we're going to shift it to the right in A2. Now, each time we shift to the left in A1, the bits go to the left. So the bit 1 there was in bit 0, and that's now been moved to bit 1. And so it's gone from a 1 to a 2, and then it goes to a 4, and then to an 8, and then it shifts another bit into bit 5, and that becomes 1, 0. And you can see all of the bits are shifting to the left in that way. But that top bit, that value of 8 that we had in the very top bit of our 32-bit register there in bit 31, well, that has been lost because it's been pushed out the register and it's completely gone. It doesn't come back anywhere. So that is what happens when a bit gets pushed out of a register through these shift commands, and that's why doubling the number 402 to 804 works. But if we shift the value 8000201 to the left, it doesn't double, it actually becomes a different value. So there are some limitations in using these shifts for multiplication. So that's shifting to the left. What about shifting to the right? Well, here you can see we've got the value 8000201. Now the top bit of that is a 1, so you could consider that to be a negative signed number, but we're not considering it a negative signed number because we're shifting logically. So as we shift to the right, that 8000201 becomes 4000100, and you can see that 1 at the very right has been shifted out and it's disappeared. It's no longer part of this register. And so each time we're shifting to the right here, you can see the values are halving and the bits are moving to the right, as you would expect for a command called shift right. Okay, so that is the logical shifts. Now, as I say, a logical shift to the left will work for signed numbers as well, providing we don't go outside of the mathematical limit of the size of the register. But when we want to shift to the right with a signed number, we need to preserve the sign, and that means we need the top bit to stay the same. And that's what the shift right arithmetic, which will work with an immediate value, or a shift right arithmetic with variable, and you can see we are using a register A3 as the number of bits to shift here, although we've set it to 1. So in both cases we've set it to 1, so we've got a simple test. Okay, and so here you can see our value 8000201 has been shifted to the right. Now the 1 that was in bit 0 has been lost again, but when we shift to the right this time, the 8 doesn't become a 4. It will shift to the next position along, but the top bit will be set to the original value of the top bit before. So the 8 now becomes a C. So this is maintaining the sign, and this is still now a negative number. And as we shift again and again, you will see that the value becomes an F, and then when we shift another bit, then the next bit in the next nibble becomes a 1, and so the top byte becomes F8. And so every time as we're effectively shifting to the right, we are dividing this signed number by 2 and maintaining the sign. And you can see that the same has happened here when we are using the immediate value instead. So they both have the same effect there. So that's what happens when we do shifts. We are effectively halving or doubling the number, and any bits that are pushed out of the register are simply lost. The alternative is rotates. Now rotates will move the bits around within the registers, but whenever the bits leave, for example, the right hand side of a register, they will return at the left hand side. So no bits are lost from the register, they're just moving around. And this can be handy for working with if you've got sort of like maybe a joystick and you're reading in the values from a joystick and the bits aren't in the position you want, so you shift them around to match what you need, but you don't want to lose any of the joystick directions, you just want them in a more convenient position. That kind of thing rotating can be very handy for. So here we're going to use roll, rotate left, and rotate right. Now these both will work with 3 registers, so the amount to rotate is in one of the registers here. And we're going to use these repeatedly, and we're going to see what happens to our test value of 8000201. Okay, well, it's not going to necessarily be too surprising, but it's not going to be the same as it was before. So first we're going to rotate it to the left. Now last time that became 4002. This time it becomes 4003. Well, why is it 3 this time? Well, because the top bit was a 1 that was making that top nibble an 8 before, and that now has become the bottom bit because it's been pushed out of the left hand side of the register and was returned on the right because it's been rotated. And when we keep shifting, you will see all of the bits keep moving around, but it's not so clear on that one. But when you will see again here, when we rotate 8002001 and the 1 gets pushed out the right hand side, it returns on the left, so the 8 becomes a C because that 1 has been pushed in to the bit 31 there. And as we keep going, if we kept going indefinitely, if we ran this 32 times, our rotations would actually end up with the exact same values that we started with. Okay, so what I've done here is I've done 16 iterations and I've done 2 rotations each time. The reason I've done that is there wasn't actually enough screen space to show 32 entries, so we've had to compromise a little bit there. But you can see here we've started with 8002001 here, and if you look at the end, you get 8002001 here, and in the same way here, you can see all the bits are shifting along. But after 32 rotations, we've ended up exactly where we're starting, and the point I'm making is, unlike the shifts, nothing is lost and nothing is added. We are just moving the bits around one register. And so there we go. So that's all we have time for today. So we've looked at a variety of shifting commands, and as I say, these are very, very useful commands. You use them all of the time in 8-bit assembly, and they're going to be really helpful for you in Mips Assembly as well. And the bit shifting commands for multiplication and division are actually faster than the multiply and divide commands in most cases. So if you're just looking to divide by 2 or multiply by 2, they are certainly worth considering. As always, go to my website, download the source code, the build scripts, have a go with them yourself. That's what they're there for. Hope you enjoy what you've seen today. Thanks for watching, and goodbye.